Alright, so now we're ready to set up this movement properly. We got it moving in the X and Y direction. And just did it manually by getting the math and doing that ourselves with just the getters on those values. And this is why I like to use Panda3D as opposed to other engines. And even in the a lot of other engines, I'll do all the stuff manually myself. Because the hard part is this: setting up a rendering, setting up the 3D rendering, the lighting. That part's kind of hard. But once that's set up, moving our character around, some basic laws of physics for forces to apply and interactions, that's really not bad to code up the simple math equations. And I would very much prefer to do it that way, which is the tutorial series I'm going to put together soon about game development. We'll go over that, because then I don't have to go to the API and try to figure out how to use this. In fact, the Panda3D API, that's kind of out of the question. So here's the one for actually walking around, the built-in thing from it. Physics walker, it handles the physics, the movements. It doesn't play sounds, but it does send a signal to play sound. But it has all of this stuff. I'm never going to remember all that stuff. And somebody else named it, so there's a good chance I'm going to have to look it up every single time, because I'll never remember the names. But if I just use the hard part they put together, and then do the easy parts myself, well, it's a whole lot easier to remember this, because the method is just what I called it. And develop a much better understanding of what's going on. And it's not like you have to do that every time, right? You do it once and then copy and paste, or do it once in a place where you can import it. So you only have to type it up once, and then it's something easy to remember, easy to remember the name. You don't have to worry about all the little intricacies that the people who developed the game engine worked into theirs to make it generalized and useful for everybody, because you know exactly what it does and fits your purpose exactly. And well, knowing exactly what it does makes it a whole lot easier to expand it. So I very much prefer to customize the math stuff after getting the initial thing going, kind of like we did here. Just manually move it instead of using what's built into the engine. And now I have this, so I can copy and paste that, or put it someplace where I can import it and just do all the math manually, which is something we're getting ready to do. So might as well start with that. We're going to need to import the math library, because we don't want to. This was just a test. We don't want to move so far in the X direction, so far in the Y direction. Oh, that somehow got changed when I was clicking around getting ready. But we don't want to just move in one direction or another. We want our X-axis on the joystick to turn the character, and our Y-axis to move either forward or backwards. And then it feels more like regular 3D movement. So we can do that by, well, we'll use something from the game engine again, something like the get X and get Y. In particular, the angles are handled with yaw, pitch, and roll. Since Y was already used, they did use an H for yaw, which is the one we'll need. That's rotation around the Z-axis. So since our character is vertical, standing along that vertical axis to turn left and right, we want to rotate around that Z-axis, so we need the yaw. And again, since Y was used in the coordinates, for yaw, the rotation, they used an H. But otherwise, we'll just get that angle, and then once we have an angle, well, our position is a 3D vector. We could have created a new 3D vector and just passed that in for this simple test. I just went ahead and passed in the X, Y, and Z manually, and then it creates a 3D vector if we pass. It's overloaded, so if we pass in X, Y, and Z separately, it creates a 3D vector on the other side, on the inside, and does that. But we could have just created a 3D vector and moved that. But essentially all we need to do is we move by a 3D vector in global space, and then obviously yaw, pitch, and roll rotations happen in local space. So we have a local angle we need to translate to a global vector. And in order to do that, we really have two options mathematically. We can either set it up as a differential equation and then solve that differential. And there's a lot of tricks there. Since we have all the information, we could probably even make it an exact homogeneous and make it even easier to solve. Or, and that would give us one way to rotate a vector around some angle. Or we could just use linear algebra and have use linear algebra to rotate a vector around an angle. If we were asking a human to solve the equation, obviously a differential equation would be a lot easier for a human to solve. But we're asking a machine, which means the linear algebra is going to be a whole lot easier to solve. So let's set this up with the linear algebra expression. And yeah, hopefully you remember some stuff from linear algebra. In particular, that if we want to rotate around a vector around an angle, I'm just going to talk about the 2D vector because our z is going to stay 0. If we want to rotate around, the new x is going to be x times cosine of the angle minus y times sine of the angle, and our new y is x times sine of the angle plus y times cosine of the angle. So we'll just apply that, and that'll give us a new vector. We'll rotate our character with the x-axis of the joystick, and then we'll rotate around that angle, rotate our current vector around that angle with that simple linear algebra expression, and then that'll give us our new x and new y position, or that'll give us our new vector, and we'll move in that new vector direction based off the y-axis of the joystick. That was a lot to say, but so yeah, kind of some complicated math, but it's basic linear algebra. This would have shown up about halfway through the elementary linear algebra class. Right after you learn to row reduce a matrix, one of the first things you do is start rotating. At least the linear algebra class I had was row reduce the matrix, and then the next thing is jump into vectors, and then simple rotations and scales to manipulate the vectors we have. So let's get started into that. Oh yeah, skew was the other one. So rotate, scale, and skew a vector. So we have the math class, so we'll be able to do the sine and cosine. So to modify this, we don't want to step in the x direction, we just want to turn in the x direction. And this is a linear speed, so when we turn, we'll want to do that with an angular speed. And I don't know whether we need positive or negative here, so I'm going to start with it positive and just adjust and see which direction it turns. And instead of step y, that's just going to be step direction. I don't think we'll need either one of these. Well, we'll get a new x and a new y, but we're going to do them very differently. So I'm just going to comment them out for now. So first thing we need is our new yaw position. So new h, since y was already used in the coordinates, they used h for yaw when they set up Panda3D. So that's going to be self.human.getH. And then we want to either add or subtract our turn angle. I'll try adding, and if it seems to be turning the wrong way, we'll just come back and subtract it. Or make this one negative. Either one would have the same result. And then we can set that in there. So self.human.set, and it's yaw, pitch, and roll. So H, and then P and R were still available. So set HPR or get HPR to return the whole vector is our yaw, pitch, and roll. So that's going to be our new yaw value, and then I'm not going to mess with the other two axes, or I'm not going to mess with the roll and the pitch, or pitch and roll. I guess I was pointing in the wrong ones there. So now our character should be facing the right direction. Let's give that a test run. I'm going to take this movement out for a second. It's just going to stay at the origin, and we should be able to rotate our character left and right at this point. So let's go give this a test run. I'm in the right folder, so Python test1.py. Run this script, and there's no need to watch it initialize, so I'll pause the video while that happens. Well, I got a typo in here, which appears to be a really silly typo. I set up the angular speed variable, but they didn't set it to anything. Since we're turning an angle, I'm just going to try 3 to start with. Actually, my first thought is, turn like 30 degrees. That first angle we start working with in trigonometry. But this is happening at 60 frames per second. So I'm going to go with 3. So then when we multiply 3 times 60 would give us 180. So we should turn halfway around in a second if we push the controller all the way around, is my thought. So 60 times a second, we're going to increase the angle by 3 degrees, which means we'll cover half of a circle in 1 second. That's how I came up with 3 for a starting point, but if that seems too slow or something, we can adjust it after we see it. And again, I'm going to pause the video while this loads. Okay, it loaded up that time. Not sure where that typo came from. That was really weird. I must have been talking and just forgot to finish it. But now if I push the controller to the right, it turned. Yes, it did turn. Push the controller to the left. So it's turning, but that's backwards from what I feel. If I turn here, yeah, we can kind of see this is the character's front. So when I think turn right, that would mean move the right shoulder backwards so that the new direction is facing to the right of the previous direction. But if I push the controller to the right, that's what I would consider turning left. And that speed doesn't look like too bad of a turn speed, so we'll go with that. But I think I want to make that negative, so I'll put a negative here and just get the negative of that value. Give it another test run just to make sure. Remember, run a test every chance you get. Otherwise, the lines of code can really add up on you. If you only change one line of code and run another test, it has to come from that single line if any problems show up. So pushing to the right, okay, that's what I would consider turning to the right. And pushing to the left, that's turning to the left. So that gets our left and right angle handled. So now we need to adjust our vector by that much. So now that we have our human turned, this line, we have our human turned to the right angle, so we can grab the angle from that yaw, pitch, and roll value, or we could, which is at this point is going to be the same as this. But I'm going to go ahead and grab it from here because I have a feeling that in the future I might do some more things between those two lines with the other joystick or with the buttons or something. So I'm going to make sure and grab it from the angle where our character is actually turned to, and I will just call that target. So that's going to be self.human.getH. So that gets our new angle, but we're using the Python math library. This is yaw, so that's an angle in degrees, and the Python math library wants it in radians. So I'm just going to do multiply by math.py divided by 180. I'm pretty sure there's also a 2 radians function in the math library, but it's not a hard calculation. I don't think it's really much shorter to type it either way. I usually just go ahead and convert it. And now that we have that, we can do our linear algebra and get our new x and y. So our target x is, well, we're just rotating it, so I'm going to assume rotation of a unit vector to make this easier, and then we'll multiply by our step size afterwards. So the general rule for programming is split it up into more lines. There's a big difference between complex and complicated. Those are terms I always use in lectures. Complex means lots of parts. Complicated means hard. Lots of easy parts are usually easier to deal with. So I'm going to assume a unit vector as our to rotate. So we'll take the new x is the cosine of our angle. We have to offset this, but I'll come back and offset it. Minus the sine of our angle, and our target y is the sine of the angle, which this is linear algebra, so vector multiplication, so really it's x times the sine plus y times the cosine of the angle. I just assumed unit vector to make that easier, but remember that's going to be x times this minus y times this, and the other one's going to be x times this plus y times this. And we have to offset it. So we're talking about angles. So a modification on the normal trigonometry, that the first class in trigonometry, we have that just xy axis, and we have those rotations. You might remember that sometimes we have to adjust where we measure it from, and this really needs to be between negative pi halves and positive pi halves, so on the right side of our unit circle. But doing it twice like this, we need to cut that in half. So instead of incrementing it, so we need to subtract pi halves, pi divided by 2, but we're cutting that in half. So then we come back a little bit, and it actually ends up being, in the end, it's going to be back to math dot pi divided by 4. So in the end, it's going to be plus pi quarters instead of minus pi halves. But my tongue got a little twisted explaining why. Hopefully that makes sense. If you think back to your first trigonometry class, and remember that sometimes we have to rotate things so that with cosine and sine, we want to be between negative pi halves and positive pi halves. But we're doing this twice, so we have to come back around to make up for that. And this isn't a math class, so we'll maybe just jump to the answer. So instead of minus pi halves, we want to add pi quarters. And that's our new range for that. So that gives us our target x and our target y value. And I should turn off word wrap because that looks weird in the coding. And now that we have those, we can actually find our new x value, which is going to be our old x value. So self.human.get x plus our step size times our target x. And same thing for y. New y equals self.human.get y plus our step size times our target y. Save that, and we can give it a test run, and hopefully this is all going to work out. Hopefully that made sense. Just doing a basic linear algebra rotation of a vector by an angle, and then after we rotate it, that gives us our new x and new y coordinates. So let's give this a run and see if that worked. And I'll pause while it loads up. Okay, so I guess first off, try moving forward or backwards. So if I push up, goes forward, and back, down goes backwards. So now the moment of truth here, push to the right, turns to the right, push up, goes forward and backwards. A little more to the right, goes forwards and backwards. Turn back to the left quite a ways, forwards, backwards, forwards, backwards. So that looks like it's all working. So there's our regular movements. And just a point I wanted to express, so we don't need these commented out ones now. We have our new X and new Y, and instead of using the built-in one, because yes, there is a built-in one, it's not that bad of math. Just some first semester of linear algebra and some basic concepts of from trigonometry, just simple vector rotation in linear algebra to convert the local rotation into the global position. And I don't ever have to worry about forgetting what this is and going and looking back up, because the method to move the character is just what I would call a method to move a character, which makes it a whole lot easier to remember. So that's the point of the tutorial playlist I'm going to make, going to be big on, is instead of use the hard parts from the engine, and don't worry about using every single thing that's built in, because a lot of it, once the renderer is there, most of the rest of it is going to be simple math equations that we can break down and set up for the computer to handle pretty easily. But that got our character rotating and then moving, instead of just moving on the XY coordinates explicitly. Kind of like what we were looking for there. So backward, forward, at any angle we want to move to. So next up, I guess, so that finishes the movement, and we'll be back to add another part to the game soon.